Hello, thanks for joining me. We are having a little adventure in the number theory direction. And today is kind of interesting because I'm going to first of all show you the sister sequence to the one I showed you last time, the plus minus sequence. So this is a variant to the prime number sequence obtained by looking at a variant of the sieve of Eratosthenes. And these two new sequences that we're playing around with have interesting properties. They are a lot like primes in some sense, and just to what extent they are like primes is going to be an interesting question for us as we go forward. But they seem to have some intrinsic interest, and I'm going to sort of expand on that, show you some more aspects of these sequences which are interesting. Now I'm going to be working with the minus plus sequence today, and I'm delighted to be joined by my erstwhile friend ChatGPT 4.0. So while we're still in this happy honeymoon stage with the AIs before they haven't taken over our lives completely, we can work with them, we can learn from them, and ChatGPT is just remarkable in the things it can do. Even though it's a large language model, you'll see it's no slouch when it comes to doing some mathematics. I'm also going to be showing you a spreadsheet kind of version of some things. We're going to do some explorations with that, and you'll see some really useful techniques for dealing with big sequences. Okay, so starting point is I've opened up ChatGPT, and I'm sort of carrying on from a prior conversation that I had with it about the plus minus sequence. So today I would like to go over the minus plus sequence. Do you remember that? Because I wasn't sure whether it sort of got the previous conversation in its memory. So it replies, yes, I remember you're working on the minus plus sequence. The sequence is generated by a specific algorithm that works similarly to the plus minus sequence, but with a small variation in how elements are removed from the working set. So I really want to go carefully over the interaction between ChatGPT and myself. I think it's really instructive. People are not appreciative yet that this is an entirely new way of doing research, okay? And it's going to take over during this intermediate period while us human beings are still sort of active, useful members of the research community. And 10 years from now, we probably will not be, or not be very much, okay? It's the machines which will be doing all the interesting work. And we'll just be going, oh, wow, did you hear what such and such machine did last week or 10 minutes ago? But in this honeymoon happy period, we can learn a lot, and it's really great for amateurs because you now have this resource that 5 years ago professional mathematicians didn't have. So you're able to do things that professional mathematicians weren't able to do until very recently. So it's exciting, if a bit scary and maybe a little bit depressing at the same time, all of these things. We have to figure out what exactly we think about this entire thing. But okay, I'm not unreservedly in favor of AIs for sure, but okay, I do acknowledge the usefulness of ChatGPT 4.0, especially with this conversation. Okay, so let's continue. Here's the outline of the minus plus sequence algorithm. So I want you to appreciate that this is not just a single conversation. This is the result of several conversations that I've had, and I've tried to explain to it what I wanted to do, and that's taken a little bit of back and forth. So there were some false starts, etc., and it's really important to not trust too quickly, to check, to monitor, to have double checks to make sure that the machine is with you. But it's also notable that the machine is really interested in formulating things clearly, laying things out. And I want you to listen to the language that it's using and just the way it's thinking, the way it's presenting information. Okay, so we've already talked about the minus plus sequence. It's now just summarizing it for us. Here's the outline of the minus plus sequence algorithm. Start with a working set WS. Actually, I called it working sequence, but okay. Working sequence, working set, consisting of numbers 2, 3, 4 up to n, and an output sequence, OS, which starts as an empty set, actually sequence. Step 1, take the first element from WS, call it X, and append it to the OS, put it at the end. Step 2, remove from WS all elements that follow the sequence pattern X, 2x minus 1, 3x, 4x minus 1, 5x, 6x minus 1, 7x, etc. So let me pause there. Last time when I talked about the plus minus sequence, what we did is we took x and we're going to remove that one. And then the next one we're going to remove is obtained from x by adding x plus 1. Here we're adding x minus 1 to x to get 2x minus 1. So that's the next one we're going to eliminate. And then after that, what we're going to add x plus 1 to that, which is bringing us up to 3x. Okay, so in the plus minus situation, what we did is we took x, we added x plus 1, and we added x minus 1 to that, so sequentially. Okay, so we're essentially eliminating x, 2x plus 1, and 3x. Okay, so the only difference in this story here is that there's minus signs here at every second step instead of plus signs. Step 3, repeat steps 1 and 2 until WS is empty. And step 4, output the OS when WS is empty. You've also generated a portion of the sequence up to 8,192, which is 2 to the 10, 11, 12, 13, I guess. The terms up to that point include values like, so here's the initial part of the minus plus sequence. 2, 4, 5, 8, 13, 16, 17, 21, 32, 37, 53, 57, etc. If you just saw that sequence, you'd be hard pressed to, to understand how this thing carries on. Very hard pressed. In fact, it's not in the online encyclopedia, although it shortly will be. Maybe one of you can do that. How would you like to proceed with the minus plus sequence? Are you interested in exploring conjectures, generating more terms, or analyzing the pattern further? Okay, and then I reply, last time we generated that up to 2 to the 15, but I wasn't able to download it. Could you please generate that again? Okay, so now it attempts to do that, okay, and it gives me an output which I check and it's not right. So I say, I think you're not generating it correctly. So I ask it to do a more modest thing, just up to 64. It does it up to 64 and that's correct now, okay. So that looks correct now. So please try again for 2 to the 15. Be careful with your arithmetic. I'm encouraging it. And now it's saying, okay, the minus plus sequence up to 2 to the 15 has been carefully generated. You can download the corrected sequence using the following link. Okay, and I've done that. And I think that's right, but, it's definitely worth checking. I will try to put a link to that somewhere. So it's just a spreadsheet, and I'll show it to you in a little while. Then I ask, can you list for us here the elements of this minus plus, let's call it MP sequence, up to 512? Please output in list form, but not in LaTeX form, just plain text. Okay. So I just want to be able to see this thing, right? So I want to scroll through this thing just so you can have a look. So 2, 4, 5, 8, 13, 16, 17, 21, 32, 37, 53, 57, 61, 64, powers of 2, 81, 93, 97. Okay. And let me just scroll slowly through here so you get a sense of what they look like up to 512. Okay, so let me know if you would like to proceed with further analysis or if there's anything else you'd like to explore. Okay, I say, great. Can you verify some congruence conjectures for me? 1. The only even numbers which occur in the minus plus sequence are powers of 2, and all the powers of 2 up to 2 to the 15 occur. 2. All the odd entries are 1 primes, meaning that they are congruent to 1 mod 4. 3. None of the odd numbers in the MP sequence after 5 are congruent to 0 or minus 1 mod 5. 4. None of the odd numbers in the MP sequence after 13 are congruent to 0 or minus 1 mod 13. So This is a good thing because it sort of forms another check on whether it's churned out the sequence up to 2 to the 15. So it verifies things and says that, okay, all these conjectures are true. True, 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 true. All of your conjectures hold for the minus plus sequence up to 2 to the 15. Okay, then I say, okay, it seems we can have a family of similar conjectures as we run through the odd elements of the sequence. You see, because the 5 and the 13 were actually the sort of the initial odd elements in the sequence. The next one is 17, and then 21, and then 37, then 53, and then 57 and 61. So I ask it, can you check that if we, if n is such an odd element, like maybe 13 or 17, then we conjecture that none of the odd MP elements after that thing, after it, are congruent either to 0 or -1 modulo that thing. Okay, so after the 17 appears, for example, I'm saying that no further guy is going to be congruent to 0 or -1 mod 17. So I'm asking it to check this. The family of conjectures holds for all odd MP elements up to 64. Specifically for each odd n up to 64, none of the odd MP elements after n are congruent to 0 or -1 mod n. And here are the verified values that it's given me. Okay, so now I want to turn to another aspect of things. So we know that all the odd MP elements are 1 numbers. Some of them are prime, some aren't. Can you list all the elements which are prime? So here are the list of the prime numbers that occur among the odd elements of the minus plus sequence. 5, 13, 17, 37, 53, 61, 97, 137, etc. So because we like to count, I ask how many such primes are there? And there are 563 such prime numbers amongst the odd elements of the minus plus sequence. Now I ask how many of the odd elements of the MP sequence have exactly 2 prime factors, including multiplicity. Now I've had to explain this to ChatGPT explicitly because previously there was a little bit of confusion. So I say that by this I mean that, for example, 12, which is 2 squared times 3, has 3 prime factors, not 2. So this 2 is appearing twice, so we'll say altogether that has 3 prime factors. So I'm asking of the odd elements which have exactly 2 prime factors, how many of these have both factors being 1 primes, and how many have both factors being 3 primes? Because we know that all the odd elements of the sequence are 1 numbers. That is, they're congruent to 1 mod 4. So if they're a product of 2 things, the possibilities are 1 times 1 mod 4, or 3 times 3 mod 4, which is 9, which is also 1. But 1 times 3 is not going to work because that's going to be congruent to 3 mod 4. So I want to know, what's happening here. And it tells me that out of the odd elements of the minus plus sequence, so 802, we're going up to 2 to the 15, have exactly 2 prime factors, including multiplicity in this sense. And 46 have both prime factors being 1 primes, while 756 have both prime factors being 3 primes. Now that's a very big discrepancy. 46 to 756. So can you list the 46 with 2 1 prime factors together with their factorizations? So these are the lists of the odd elements in the minus plus sequence that have 2 prime factors, both of which are 1 primes. The smallest one is 1,681. So when I was first looking at this, looking at, let's say, the first 1,000 up to 1,000 or to 1,500, you're not going to find any odd numbers which are products of 2 1 prime factors. So actually, initially, I sort of said, well, maybe that's always the case, okay? But it's not always the case. There are some cases where we have 2 1 prime factors, but not relatively that many of them, at least not in this range. Okay, so here are the the values. So that's sort of interesting to me. I'd love to know whether that carries on. Like, I wonder if that sort of imbalance is just sort of a temporary thing when we're relatively small, or if it maintains itself as we go further and further into the MP sequence. And if it does maintain itself, there's something to be explained here. Well, even at this stage here, we're going up to 36,000, so that's already a pretty big range. So why is it that the product of 3 primes, a 3 prime times a 3 prime, is like more than 15 times as numerous as the product of 1 prime times a 1 prime? So then I ask, how about those elements with exactly 3 prime factors? Can you list them and their factorizations? How many have all factors 1 primes? So if the product of 3 primes is going to be a 1 number, okay, it means the possibilities are 1 times 1 times 1, or 1 times 3 times 3. Okay? So here's a list of elements from the minus plus sequence that have exactly 3 prime factors along with their factorizations. Unfortunately, none of these elements have all prime factors as 1 primes. So we're seeing a similar phenomena when we're going to numbers which are products of 3 primes. In this case, up to this range, none of them have all factors being 1 primes. Okay, anyway, here's an Excel spreadsheet which has the list of regular, honest, good old-fashioned primes, 2, 3, 5, 7, 11, 13. And it's been given to me by ChatGPT, and it goes down to, let's see, down to 16,000, and there's 1,900 such entries there. Okay, and just beside it, I've also put the differences. So this thing here, it's equation, it's A3 minus A2. This next one is A4 minus A3, etc. So these are just the successive differences. In the number theory world, these are called the gaps between the primes. And the gaps are very interesting. You know, there's a lot of work trying to understand, you know, what the sort of statistics of these gaps is. How big can they get, relatively speaking, and you know, what's the distribution, etc. So let's just scroll down this so you get some sense of the gaps. Okay. Of course, this is great for amateurs to ponder. You will not be the first to have done that, right? Like thousands of people have stared at this over and over again. I remember being in grade 8 or something like this and making a difference table for the prime numbers. I think probably every aspiring mathematician does this. Well, what's the pattern? Let me see if I can figure out a pattern. Okay, anyway, so I just want to sort of alert you, because some of you will have done the algebraic calculus. Those of you who have not done the algebraic calculus will, of course, be aspiring to do that, right? Learn calculus properly. And the discrete calculus plays a pretty big role in that. And this, from a calculus point of view, is just the first differences of this original sequence. And it's just, useful to realize that you can just keep going. So if I go up here, for example, and then I say entry, let's say this one here will be this one minus this one, okay? Okay, so it's 1. Now, one thing I can do is I can just grab this little thing down here and carry on, okay? And I can go all the way down to the end, and I would get all the successive differences. So these are the second differences, okay? Of course, it's, they're mostly even numbers except for the first one, but anyway. And if you wanted to go further, we could just repeat the process, but even a more nifty thing is just to grab the thing and to extend it over in this direction. So if we look at this entry here, this is equal to the difference between C3, which is this one, C3, and C2. And this one here is the difference between D3 and D2. So one thing we could do is we could grab all of these, grab that whole row, and I'm going to drag the whole thing down. I won't just go there. Okay. So I've now just at one stroke created sort of multiple differences. Okay. And okay, that's pretty cool. The top row here is especially important if you've taken the algebraic calculus. It gives us essentially the Gregory-Newton formula for recovering a polynomial sequence. These are sort of the crucial coefficients that you use with the Harriot basis elements to recover an arbitrary sequence. So this is sometimes called the binomial transform of the original sequence. You could do this for any sequence, of course. So this sequence that's appearing along the top row of the successive differences is a kind of a transform of the original sequence, and it's of course of independent interest. So having said all that, let us turn to, here is, this is pretty small, I'll bet. Can I make that a little bit bigger? Okay, so there we go. There's the minus plus sequence, okay? 2, 4, 5, 8, 13, 16. And this is the spreadsheet that ChatGPT has just created for me. Another great application, right? So I have the spreadsheet here down to, presumably, 32768, which is 2 to the 15. So, for example, right, obviously we're going to be wanting to sort of examine differences of this thing. So let's just actually do this. So let's say this is going to be equal to this entry minus the previous entry. Okay? And it's a 2. And I'm just going to drag this thing. Might actually go right. Well, I don't have to go all the way bottom. Okay, I've got to 20,000. That's probably enough. Okay. So let's just admire this. So this is like the equivalent in the minus plus world of studying the gaps between primes. Okay, so to try to understand the regularity or otherwise of this sequence, you could study these gaps and and try to come up with some statistics for them. You could reduce them various mods. You could do various things. We'll talk a little bit more about that in our next video. And of course, if you wanted to get higher differences, we could just drag this thing over like this. Okay, let's just check that this thing here is equal to B3 minus B2. So that's giving us the difference of the B table, or the B column. And then we could take the whole thing, maybe from here, from here up to here. Okay, drag the whole thing. I'll just go down here. And we get a difference table for the minus plus sequence. Okay, and then along the top row here, the 2, 2, minus 1, 3, minus 3, minus 1, 9, minus 16. So that's also got to be in the online encyclopedia at some point, right? So that's the binomial transform of the minus plus sequence. But there's potentially all kinds of things to stare at here. Stare at these things and see if there's anything interesting, see if there's any interesting patterns. So there's a lot to do here, especially having a lot of fun for amateur mathematicians.